On this video, we're going to talk about Section 8.3 in our book, Relative Rates of Growth, which is a topic we've talked about in the past, last year in AP Calculus AB in terms of orders of magnitude of functions. So e to the x and natural log x are the standards of comparison. If a graph has a scale where one tick mark on our graph is going to be 1 centimeter, then let's consider how we would graph e to the 43. So 43 centimeters is a little bit less than 2 feet. E to the 43rd is about 4.7 times 10 to the 18th power, which is about 5 light years. Proxima Centauri is the nearest star to the sun, and that's about 4.3 light years away. So to graph y equals e to the x to scale, we would, on our graph, go right 2 feet and up just past Alpha Centauri. So that just gives you an idea of how fast exponential functions grow. And that's why, at least for now, they're the highest order of magnitude function that we have encountered. Now, by the same token, if that's how fast an exponential grows, then the y equals natural log x, remember, is the inverse function of e to the x. So that means that if the point 43 e to the 43rd is on the exponential, then if we switch that around and make the x-coordinate e to the 43rd and the y-coordinate 43, that'll be a point on our logarithm graph. So that means we're going to go up a little, about 2 feet, and then right all the way past Alpha Centauri. So that gives you an idea of how slowly a logarithmic function grows. So those are the standards. E to the x or an exponential are the highest order magnitude functions, and logarithms are the lowest. They're the slowest growing functions, and polynomials fall somewhere in between. So our order of magnitude goes logarithms are the slowest, polynomials are in the middle, and exponentials are the top of the food chain. So a definition, let f of x and g of x be positive for x sufficiently large. We say that the function f of x grows faster than g of x as x goes to infinity if either we can look at it as the limit as x goes to infinity of f over g. If that goes to infinity, that means the numerator function is getting much bigger, much faster than the denominator function, and so f grows faster, or f is a higher order magnitude function. If we switch the order and put the g on top, then if the limit goes to 0, that makes us say that f is growing faster than g, or f is a higher order magnitude function than g. And the second thing is f and g grow at the same rate if their limit goes to some finite number, not 0. So that's what we mean by same order of magnitude. So for example, 2 to the x and x, we know that 2 to the x is going to be bigger than x for any positive value of x, but we still say they're the same, they grow at the same rate, or they're the same order magnitude function because their limit as x goes to infinity is a constant, 2, which is not 0. So we say they're the same order of magnitude. So if f grows faster than g, that is, if f is a higher order magnitude function than g, then g is negligible compared to f as x goes to infinity. So, for example, if we take the limit as x goes to infinity of f plus g over f, we can split that apart and make it f over f plus g over f, and we can see that that f over f, of course, is just going to be 1, but g over f is going to go to 0, and so that's what we mean it's negligible. It's not going to make any difference. That's why you see in the blue the end behavior of any polynomial. If we want to know what is the graph of some polynomial function going to be as x goes to infinity, what happens at the ends is completely determined by the highest power of x and its coefficient. And that we called last year the leading coefficient test. So if we are curious about what is the graph of this polynomial going to be at the ends, way out to the right and way out to the left? Well, we know all we have to look at is the leading coefficient. So the highest power of x is x to the third, so it's going to act like a cubic. Since it's multiplied by a negative, it's going to act like a negative cubic, a reflected cubic. So that means whatever it may do in the middle, we don't know, but way out there to the right, it's going to look like it's going to go down, and way out there to the left, it's going to go up, because there's our cubic, and a reflected cubic is going to fall from left to right. So we know the end behavior based on the leading coefficient and the highest power of x, because the other powers of x are negligible compared to whatever's the biggest. So we can use Lhopitals rule to make this decision or to compare these. Now we know these, so hopefully we know that an exponential is a higher order magnitude function than a polynomial, but we can use our Lhopitals rule to kind of affirm that. So if we take the limit as x goes to infinity of, say, and we want to go x squared over e to the x, it doesn't matter which order we do, then this is going to be infinity over infinity. I'm not going to be particular about writing this down the way you'd need it on an AP exam, but I'm going to say we're going to go use Lhopitals rule, and so we would get the limit as x goes to infinity of the derivative of x squared is 2x, and the derivative of e to the x is still e to the x. That's still going to be infinity over infinity. So we could use L'Hopital a second time, and that's going to get us to the limit as x goes to infinity, and the derivative of 2x is 2, e to the x is e to the x, and now you can see that's going to go to 0, which means our denominator function grows faster than the numerator function. Okay? Same idea with our 3 to the x compared to 2 to the x. If we take the limit as x goes to infinity of 3 to the x over 2 to the x, in this case, I don't know that we necessarily need L'Hopital's rule. We can think of this as the limit as x goes to infinity and write that as 3 halves to the x. Now you can see that a number that is bigger than 1 times itself over and over and over again is going to grow large without bound. It's going to go to infinity, which shows us that the numerator function is growing faster than the denominator function. For a natural log x and an x squared, we can again take the limit as x goes to infinity of natural log x over x squared. That is going to be infinity over infinity initially. So we'll use our L'Hopital's rule, and we'll take the limit as x goes to infinity, and we'll have 1 over x from the derivative of natural log x, 2x from the derivative of x squared. As x goes to infinity, the numerator is going to go to 0, and the denominator is going to grow large without bound, which is going to make the limit be 0, which means that the logarithm is a slower growing function than the x squared. To show that x grows at the same rate as 3x plus sine x, we can take the limit as x goes to infinity of x over 3x plus sine x. We can see that this, as x goes to infinity, that's going to be infinity over infinity. And I think we're better off here. Actually, I'm going to change the order of this because otherwise it gets a little tougher. I'm going to put the 3x plus sine x in the numerator and the x in the denominator. So that is going to be infinity over infinity initially. If we split that up, we can think of that as the limit as x goes to infinity of 3x over x plus the limit as x goes to infinity of sine x over x, and the 3x over x, that's just going to go to 3, and this is going to go to 0. And so because that is a constant, not 0, that shows that they grow at the same rate. Kind of an interesting one, log base a and log base b of x. We're going to use our change of base, and we can say the log base a of x is the natural log of x over the natural log of a. That's our change of base. Similarly, logarithm base b of x is going to be the natural log of x over the natural log of b. So if we take the limit as x goes to infinity of log base a of x over log base b of x, that's taking the limit as x goes to infinity of natural log x over natural log of a over natural log x over natural log of b, which is going to be that limit as x goes to infinity of natural log x over natural log a times, we'll multiply by the reciprocal, and we will get these things that are going to infinity to cancel, and that will become just natural log b over natural log a. Remember, those are both constants, so that's just going to be a constant, which shows us that these are actually growing at the same rate. They are the same order of magnitude. Okay, now we have this idea that's called the transitivity of growth rates. So transitivity is, what that means is, for example, equality is transitive. So if A equals B and B equals C, then we know that A is equal to C as well. Inequalities are also transitive, so something like if A is less than B and B is less than C, then it must be true that A is less than C. That's the idea of transitivity. So as applied to growth rates, then it means if f grows at the same rate as g as x goes to infinity, and g grows at the same rate as h as x goes to infinity, then f grows at the same rate as h. So this is kind of leading to a kind of a technique that is sometimes used in trying to determine these limits. So we want to show that f of x and g of x grow at the same rate. Rather than comparing them directly, what we would do is, or it's kind of really, we would say, where this might come up is you would look at this and say, well, this is going to act like, since x squared is the highest power of x that appears in this expression in the radical, and the square root of x squared is going to be an absolute value of x, but at least it would be an x to the first. So if we're talking about as x goes to infinity, we're not worried about the negative part of that. So we think that's going to act like x. And similarly here, when we square this out, what's going to emerge out of this squaring that out is going to be that 2 square root of x quantity squared, which is going to be an x to the first. So we might suspect that these both really act like an x. They're going to be the same order of magnitude as an x. So the way we can do that is we can take the limit as x goes to infinity, and we'll first take our f of x, which is this x squared plus 5, and we'll compare that to x. So what we can do here then is we can bring that x into the radical. So we can make this be the limit as x goes to infinity. And when we bring this x into the radical, we're going to call it the square root of x squared. And so that's going to become the square root of x squared plus 5 all over x squared. And we can do this in fewer steps, but we can then look at splitting that apart and making that the square root of x squared over x squared plus 5 over x squared. Now, as x goes to infinity, x squared over x squared is going to approach 1. It's always going to be 1. The 5 over x squared is going to get smaller and smaller and go to 0. And so our limit is going to go to the square root of 1, which is 1. Now we can also do that with the second one. So we're going to take the limit as x goes to infinity of our g of x, that 2 square root of x minus 1 squared all over x. And we'll see if we can't get a constant there as well. So we could think of this. I mean, there's several ways you can do this, but one way to do this might be to say, well, let's bring this x into that group. So if we're going to bring it into the square, that's going to be 2 square root of x minus 1 over, we're going to have to call that the square root of x, quantity squared. And then we can think of that as being the limit as x goes to infinity of, and then we can separate that out and call that 2 square root of x over square root of x minus 1 over square root of x, that whole thing squared still. Hopefully you're still with me. Now as x gets really, really big, then, well, we can see even no matter what for x, that these square root of x's will cancel. As x gets really, really big, this 1 over square root of x is going to go to 0. And so this is going to look like 2 minus 0 squared, which will be 4. Okay, so that's transitivity. It's a technique that's sometimes used, more of a formal technique for trying to evaluate limits of some of these things as x goes to infinity. We're going to talk about sequential versus binary. So computer scientists measure the efficiency of an algorithm by measuring the number of steps the computer must make. For example, there are 26,000 words, more than 26,000 words, beginning with the letter A in Webster's dictionary. One way to search for a word is sequential. So you might be given a word that starts for A and you're going to try to find it, and that would just be starting at the beginning and just looking through one word after another until you can match it. Of course, if you end up with the last word or one of the last A words, then it's going to take a lot of steps. It could take as many as 26,000 steps. Versus binary, which says go to the middle and use the order of the alphabet to then, compare the words you're looking for with that word in the middle. That will allow you to eliminate 13,000 choices because you're going to know that the word you're looking for is either in the first half or the second half. So then, after you've eliminated one of those halves, then go to the middle of the remaining group and repeat the process. So by using that binary strategy, then you can see that because 26,000 is in between 2 to the 14th and 2 to the 15th, that it will take at most 15 steps to find that letter, that word that you're looking for out of the 26,000 possible choices. So in general, if 2 to the m minus 1 is less than n, is less than 2 to the m, that is, if you can find the powers of 2 that our number is in between, our number of choices is in between, then if you take the logarithm base 2, that's going to put you in between m minus 1 and m. So what this says is the maximum number of steps. What this symbol means right here is the greatest integer less than or equal to the logarithm base 2 of n. So if this number was, like we saw up here, was something like the logarithm base 2 of 26,000 is going to be 14 point something. I don't know what, I'm just going to make it up, say 3,1. What this symbol means is the greatest integer less than or equal to this number. So the greatest integer less than or equal to 14.31 would be 14, and so by adding 1, that's going to give us that larger choice. That's what we're looking for, is that value of m. Okay, very good.